All right, I want to give you a little help with some of these problems. This first problem asks for the normal force. That is the box, that's the ramp's force on the box, the ramp's upward force in the box. Well, how hard does the ramp exert, how much force does the ramp exert on the box? It's exactly equal to the box's force on the ramp, because the sum of the forces in the y direction for the box equals 0. So, so the down forces on the box equals the up force in the box. What's the down force in the box? It's the perpendicular component. That's this perpendicular component. What is the up force in the box? That's the normal force. Do you remember when you drew the normal force on that big diagram of the box on the ramp? I said, how long do you do the normal force? The normal force is equal to the perpendicular component, which of course is, let me just erase this, make it look good. The perpendicular component is FG cosine theta, where that's theta right there. Okay, so how big is the normal force? Well, the normal force, because the sum of the forces in the y direction on the box equals 0, the normal force is equal to the weight force. The up force equals the down force. Let's see if I can draw the normal force in just as big. Let's see, I'll do my best because I don't have a ruler here. There's the normal force, and the normal force is equal to the perpendicular component. So every time now you ask for the normal force, it's so easy. It's simply either FG cosine theta, or if they give you M, it's MG cosine theta. Every time you ask for a normal force, you do that. So that helps you with that one over there. Now all you have to do to get the normal force is plug into this equation here. Now we don't have M, we have FG. How do I know? Because it's a 30 Newton box. That's FG. FG, because it's newtons. Let me see if I can help. Here's another kind of weird one. I don't have a question like this at number 2 on the test. It's a little too weird to put on the test just now, maybe later on. You've got a pendulum, and this pendulum is hanging from a string that's non-zero. All our strings in the test, all our strings so far have had no mass. It's non-zero. So this has got some mass M, and this it's got mass. This has got a mass. The bob has mass as well. What's true about the tension? The tension has got to be greatest at the top, because at the top it feels the tension, the mass of the string and the mass of the bob. So the greatest tension's at the top and the least tension's at the bottom. Greatest tension is at the top. So there's an answer for that one there. Let me give you another. You already looked at this one. Now, how do you do this one over here? You draw a free body diagram. We went over that. It's got a weight of W. It's got a T, what's that called? T2 going this, yeah, T2 going this way. T1 going that way. This angle is theta. So that angle is theta as well. Forms the Z. 2 parallel lines cut by a transversal. There, step 1 in our 3-step method is to draw the free body diagram. And so now what do? Well, you do what you always do. Sum of the forces in the x direction equals 0. And you do that. And you do, I'm not going to give it to you, sum of the forces in the y direction equals 0. And you bring them together. I think this one over here. I'm not sure. One of these two, 5 or 6, I think you have to use that sine over cosine creates tangent. I'm not sure which one it is. So do this one and this one. Work that out. The left forces equal the right forces. I didn't label this. This is T2 and that is T1. You should always label your free body diagrams real well for you. It'll help you solve. So these two, sum of the forces in the x direction equals 0, sum of the forces in the y direction equals 0, will give you the answers to 5 and 6. Okay, here's another one of those weird problems that I won't put on the test. It says the rope has I'm going to do this one for you too, because there's a lot of homework. The rope has a 60 newtons, and the box is 90 newtons. So what is the ratio of the tension on the top of the rope, called T-top, to the T-bottom? T-top, yeah, T-top to T-bottom. Okay, T-top. Well, right here, the tension at the top has got to be 150 newtons because it feels the weight of the string and the weight on the bottom. So these two get added up. The tension on the bottom of the rope only feels the 90 Newton weight. So you can work that one out to a solution. Let's see what else I could do for you. All right, let's see. Oh, there's that normal force question I told you. What is normal force? The normal force always equals mg cosine theta or fg cosine theta. Why? Because what's the physics on that? The sum of the forces in the y direction equals 0. So the box's force on the ramp, which is mg cosine theta, equals the ramp's force in the box. You got to include that. That's the physics. Can't just go right down to there. So you've got, what do we've got here? Oh, we've got m. So we're gonna have to use this one here, aren't we? I call it big mg cosine theta, I guess. All right. What is now? How do you do this? What is m in terms of m and theta? Well, what you got to do is what we keep doing is do for both boxes. This is x and y. Sum of the forces in the y direction equals 0. And this is x and y. Sum of the forces in the x direction equals 0. And you work it out. There's wait, we'll call this, what are we calling this? I guess we'll call this T, because we don't know what it is. It goes over a massless pulley. We'll call that T as well. And so we can bring the two equations together and hopefully be able to find m in terms of big M and theta. This is, of course, theta. It's big M, little m. So you do this, and you do this, and you bring them together. Okay, what else can I do for you here? There's that normal force question again. Sum of the forces in the y direction equals 0. So the box's force on the ramp equals the ramp's force on the box. So now look at it says m. So I think I'm going to use mg cosine theta because it says m. It's a 3 kilogram box. So I'll just do that. And I think I gave you quite a bit of help here. There were a lot of problems. So let's stop this and we'll good luck on it.